let's have a look at argument indexing, often simply called indexing. And we start with the observation that depending on the arguments of a predicate, only a subset of clauses may be applicable. And of course, Prolog must preserve generality and also ensure efficiency. That is, we expect to be able to use a predicate to enumerate solutions and also to test concrete solutions. And all of this should be as fast as possible. So, in particular, if some arguments are already instantiated, then we expect the Prolog system to quickly determine which clauses are applicable and to try only that subset of clauses. And one way to do this is to consider the head of each clause, and ideally in such a way that a complete scan of all clauses is avoided. So instead of a complete scan of all clauses, we want the Prolog system to determine as quickly as possible the clauses that need to be tried, and then to consider only that subset of clauses. And argument indexing exists exactly for this purpose, that is, to quickly narrow down the clauses that need to be tried for a given goal. And the key idea of argument indexing is to use efficient data structures for clause lookup. Very often hash tables are used for this. And of course other data structures would also be perfectly suitable. And to be perfectly clear about this, argument indexing is performed purely for the sake of performance. That is, argument indexing doesn't affect the meaning of Prolog code. So this is similar to indices in databases, which aim to make queries faster without changing their meaning. And in fact, some database systems would be well advised to use Prolog indexing as some form of inspiration, because in most Prolog systems, indexing happens completely automatically. So, as Prolog programmers, we don't even have to know much about indexing to benefit from it. However, in some Prolog systems, declarations are necessary to benefit from the full potential of indexing, and that's again similar to database systems. And in general, the sophistication of indexing depends on the Prolog system. So it's always good to read the system documentation to find out what we can expect from a given Prolog system. So let's consider an example. Let's say that we have a predicate P with 2 arguments, and the predicate shall have 4 clauses. More precisely, let's say that the predicate consists of these 4 facts. Of course, it could also consist of rules. However, and importantly, for argument indexing, only the head of each clause matters. So, for the sake of simplicity, let's consider only this definition with 4 facts. And on the understanding that the same considerations apply also for rules. And of course, a predicate must work in all directions. So, Prolog must make this general, in that it must be able to generate all solutions and at the same time also efficient. In particular, if partial information is already provided in queries, then that information should be automatically used to quickly narrow down the search to only the relevant clauses. So, for instance, in the most extreme case, when we ask a yes or no question about these facts, where all arguments are instantiated, then we expect a very quick answer from the system that ideally avoids a linear scan of all facts. And this desire to avoid a scan of the entire database is the motivation for argument indexing. And to understand indexing, let's make a few observations about this sample program. First, we need a basic understanding of choice points. Choice points are a mechanism that's used by the Prolog system to remember alternatives that must be tried on backtracking. So, choice points are created internally by the Prolog system. For instance, suppose we have a predicate R where our sample predicate P is used as one of the goals, and possibly some other goals also occur. And in fact, it doesn't even matter in which context P is used, so we may just as well regard the goal P in isolation. For instance, this is the most general query where all arguments are fresh variables, and the following considerations apply equally if this goal is used in a different context, for example as part of a predicate definition. Now, which clauses must be considered to find solutions? Well, clearly in this case, all clauses are applicable, because each of these clause heads unifies with the goal. And note that I say unifies, not matches, because Prolog uses unification when considering applicable clauses. However, we sometimes also say a clause matches, although strictly speaking, matching only means one-sided unification. So Prolog must somehow try each alternative and show us all solutions. And Prolog does this by considering the alternatives one after the other. We get the first solution from the first clause, and a choice point remains. Because the Prolog system has internally remembered that other clauses also apply, and to get all solutions, the other clauses must also be tried. And as is characteristic for Prolog, we don't get everything at once, but sequentially one solution after the other on what is called backtracking. So Prolog asks us what to do next. And when we press space, then we get the next solution. And again, a choice point remains, because other clauses, or more precisely, other clause heads, also apply for this goal. So we press space again, get another solution, and so on. And we say that Prolog enumerates or generates all solutions on backtracking. And choice points are used internally to remember which alternative clauses need to be tried. So this is the situation for the most general query. Now let's specialize the query. This means that instead of a variable, let's use a more concrete term. For example, let's try a query where the first argument is no longer a variable, but the atom A. So let's consider just this first argument, the atom A, and let's consider which clauses apply for this more concrete query. And obviously now only those clauses must be considered where the first argument in the clause set is unifiable with the atom A. And in our sample facts, there are exactly two clause sets where the first argument unifies with the atom A, namely the first two. So in this case, by considering just the first argument, we can already narrow down the applicable clauses to the first two clauses, because the other clause heads are certainly not unifiable with this goal, on the grounds that already their respective first argument is not unifiable with A. And when we pose this query, we get the first solution, which corresponds to the first fact in our sample program, and a choice point is left, because the system has remembered that another clause is also applicable. And when we press space, then we get the second solution, which corresponds to the second fact in our sample program. And this now ends with a dot. And this means that what we see here is the definite answer. In other words, Prolog is certain that no other solutions exist, because no choice points remain. And that's remarkable, because there are two additional clauses, and the system has determined already at this stage that these other clauses don't need to be tried. And that's of course useful in itself, because it means that we can more quickly continue with other work, post further queries and so on. But more importantly, this is a necessary precondition for important further optimizations, because some optimizations are only possible if no choice points remain. Most notably, tail call optimization, and as a special case, tail recursion optimization, only applies when no choice points remain. And so, to improve performance of Prolog programs, it's important to minimize choice points. This means, ideally, to already prevent their creation. Now, who should do this? I mean, is this something that we as programmers must do, or is this something that Prolog should do for us? And clearly, this is something that first and foremost Prolog should do for us, possibly and only if absolutely necessary, with small assistance from us, because we must be able to focus on other tasks. And in order to focus on more complex things, we really need all the help we can get from the Prolog system. So the Prolog system should automatically make it as convenient as possible for us to write efficient Prolog code. And argument indexing exists for exactly this purpose. So argument indexing is a performance feature that Prolog systems implement. And impressively, argument indexing can turn a linear scan of all clause heads into a fast, constant time lookup. For example, let's try another quite concrete query, where the first argument is instantiated to B. Then in our sample program, there's only one applicable clause head, because there's only one clause where the first argument is B. So in our case, we can tell already from the clause heads that only one clause needs to be considered. And the Prolog system arrives at the same conclusion, because when we post this query, then we get a concrete solution. So the query succeeds with the substitution y is c. And moreover, we see from the answer that there is no other solution, because no choice point remains. And when a query succeeds without leaving a choice point, then we say that the query succeeds deterministically, or that this is deterministic success. So to repeat, the Prolog system has determined automatically that only a single clause applies in this case. And moreover, this can be done without scanning the entire database. And clearly, that's good, because this improves time and space efficiency, because this means that no choice points remain. And moreover, in this concrete case, choice points weren't even created. So that saves time, because creating choice points, of course, costs a bit of time, because they must be allocated, maintained, and so on. And even more importantly, and as already mentioned, if choice points are accumulated, then this may prevent further performance optimizations. So it's very good for performance when the system can quickly narrow down the set of applicable clauses and prevent the creation of choice points. So how does a Prolog system do this? Well, from the cases we've seen so far, it looks easy enough, right? Simply take a look at an argument that's instantiated and quickly narrow down the applicable clause heads, right? But that's not all there is to it, because, for example, in general, it's not enough to analyze a single argument. For instance, let's consider the query P of A and B, which is very specific in the sense that the arguments are ground terms. So this query is a simple yes or no question. And let's consider the first argument, which is A. So there are two clauses that apply, namely the first two clauses. And if we consider the second argument, which is B, then there are again two clauses that apply, namely these two. And accordingly, when we post this query, we get success and a choice point remains. And when we press space, then the system tells us false. This means that there are no further solutions. And this in turn means that the choice point was redundant, because the alternative clause that was considered on backtracking turned out to not apply after all. And to detect such cases, the system has to take both arguments into account, because clearly in our sample program, only a single clause, namely the first one, applies for this query. So why hasn't the system detected this earlier? Well, the reason is that there is a trade-off between indexing speed and indexing complexity and practical usefulness. And Prolog systems choose different ways to solve this task. For example, there are Prolog systems that implement complex indexing schemes to minimize the number of choice points. And they accept that this may slow down the system a bit, and that this also increases the complexity of the implementation. Whereas other systems implement fast and simple indexing schemes, which require more effort from Prolog application programmers to reduce choice points. So, which indexing techniques are used by Prolog systems? And I stress again that this is system specific, so there's nothing that requires a Prolog system to implement a particular indexing scheme. However, the baseline for indexing is first argument indexing. This means that the Prolog system indexes on the principal functor of the first argument of each predicate. And I say baseline because we expect every Prolog system to do at least this. And in a sense, first argument indexing would be sufficient, because if a Prolog system provides this, then we can emulate more sophisticated indexing schemes on top of it, with the drawback that it would require manual effort from Prolog application programmers. And that's a pretty significant drawback, because we want to write Prolog code that's natural for us as humans, and the Prolog system should still run such code efficiently. And accordingly, many Prolog systems go beyond the bare minimum and implement, for example, deep indexing. This means that arguments are inspected more deeply. For instance, if we have these two clauses and then pose this query, then the principal functor of the first argument is f/1. And if the Prolog system only considers the principal functor, then both clauses seem applicable. However, a Prolog system with deep indexing can detect that only a single clause applies, because there is an inner term with functor g. And when this is considered, then only one of the clause heads applies. So for this particular query, the second clause can be ignored entirely. And further, there is multi-argument indexing. This means that pairs, triples, and other combinations of arguments are taken into account. Then there is just-in-time indexing, which is also abbreviated as JIT indexing. This means that indices are created dynamically, based on which arguments are instantiated in queries, and also based on which predicate arguments are suitable, or at least promising candidates for creating indices. And the key idea is the same in all these techniques. Namely, the clauses are analyzed and the Prolog system creates fast lookup tables to quickly determine which clause heads unify with a query. For example, suppose we have a new sample predicate P and a clause where the first argument is the atom A, followed by any other arguments and any clause body. And a second clause where the first argument is the atom B, and a third and last clause where the first argument is also B. Then for fast lookup, the system may, for example, build a hash table that states if the first argument is the atom A, then only the first clause is applicable. And if the first argument is the atom B, then the second and third clauses are applicable. So this is one way to implement first argument indexing. And of course, on the understanding that the system automatically updates such tables as needed. And as a consequence, this means that indexing has a cost, because it takes time to construct and update the hash tables when needed. And due to indexing, asserting and retracting clauses is slow. Of course, I don't mean slow in an absolute sense. Rather, I mean that indexing slows down these features. And indexing is also the reason for the saying that the Prolog database is very good for reading data, but not so good for repeated changes. However, on the other hand, Prolog is of course also quite useful for database use cases. So in applications where we need to read and write large amounts of data, we expect Prolog to perform reasonably well too. And in fact, for a wide range of database use cases, we expect a performance from Prolog that's comparable to dedicated database systems. So maybe it's best to focus not so much on performance here, but rather to stress that generally we prefer to model changes between things as relations between predicate arguments, because using relations is more general and amenable to logical reasoning. And in addition, it's also often faster than dynamically asserting and retracting clauses, precisely because changing the database dynamically incurs the overhead of argument indexing. So, on a general note regarding this topic, we prefer to use the pure monotonic subset of Prolog, and we generally avoid changing the Prolog database dynamically. Now, why are we even interested in argument indexing? I mean, I just said that Prolog should do this automatically. So why do we care about it? And the reason is that we can apply various techniques to benefit from indexing. The most important ones are, first of all, to use clean data structures, as opposed to so-called defaulty ones. A clean data structure means that we use dedicated functors to distinguish different cases. For instance, if we use Prolog to describe arithmetic expressions, then we distinguish various cases, such as concrete integers, addition, multiplication, and so on. And the important point here is to symbolically distinguish the cases so that each case is indicated by a dedicated functor. For example, in this representation, I've used this number sign or hash symbol as a wrapper to represent a concrete integer I. And the other cases, such as addition and multiplication, are distinguished by their own dedicated functors. So, using clean data structures is an important precondition for argument indexing. And we'll consider this in more detail on another occasion. Another thing we can do to benefit from indexing is to pool unifications into clause heads. For instance, if we have a predicate P of x, where the constraint x is equal to a occurs as one of the goals, then we can express this explicit unification equivalently by removing the goal and stating this directly in the head of the clause. Because argument indexing can now look at this argument a and distinguish this case from others. And it's reasonable to demand that a Prolog system should perform such obvious tasks for us, because especially beginners will often use explicit unifications. And in some cases, also expert Prolog programmers may prefer explicit unifications. For example, in cases when putting everything into arguments would result in lines that are too long, or for example, when Prolog code is automatically generated. And a Prolog system should also make such code fast, so ideally this happens automatically. Then we can exchange arguments to benefit from indexing. Let's take a closer look at this. First, exchanging arguments is a workaround, and it's often used for Prolog systems that only implement first argument indexing. Take for example maplist with 2 arguments. This shall hold if and only if the predicate that's specified in the first argument holds for all elements of the list ls, which is the second argument. And we really do want to specify the predicate that must hold as the first argument, because we want to make nested calls possible, such as maplist of maplist and so on, which describes a relation that holds for lists of lists and so on. So we can, for example, implement maplist as first, maplist holds for the empty list. And in that case, the predicate that's specified doesn't matter. And second, if there is at least one element L in the list, then the predicate must hold for L and maplist must hold for the tail ls. And that's all. And when we post, for example, is it the case that all elements in the empty list are different from the atom A, then Prolog tells us, yes, that's the case. And we see that a choice point remains. And on backtracking, the Prolog system tells us that there are no further solutions. And this means that the choice point was redundant. And the reason for this is that first argument indexing can't tell the clauses apart, because in this concrete query, the first argument is the term diff of A. And in this concrete implementation of the predicate, both clause heads unify with this query if we only consider the first argument. Now, Interestingly, if we consider the second argument of the query, then it's clear that only one of the clause heads unifies with the query, namely the first one. And so, a solution that suggests itself is to change our implementation of the predicate by having a main predicate map list with the desired argument order, and have that main predicate invoke an auxiliary predicate, say maplist underscore, where we use the list as the first argument and the predicate as the second argument. And the auxiliary predicate is defined as before, just with the arguments exchanged, okay? And now, first argument indexing can distinguish the clauses, because in the first clause, the first argument is the atom nil, and in the second clause, it's a compound term with functor dot and arity 2. So, at first sight, this appears to be a nice way to benefit from argument indexing. However, it can lead to convoluted Prolog code. For instance, consider maplist with 3 arguments. So we now have a predicate that must hold for corresponding pairs of elements in 2 lists, A's and B's. And we may use an auxiliary predicate again, maplist underscore. And here, to benefit from argument indexing, we may want to use A's as the first argument, or we may use B's. So which shall we use as the first argument, A's or B's? Because either of these arguments may be instantiated, and either may therefore be useful to distinguish the clauses. So we may be tempted to test which of these arguments is sufficiently instantiated and then use that as the first argument. However, testing instantiation of an argument is extra logical and in general leads to wrong results. So a good solution for such cases is, instead of manually exchanging arguments, is to ask your Prolog vendor to implement just-in-time indexing or better indexing schemes in general. Because, as already mentioned, when programming in Prolog, we'd like to take all the help we can get from the Prolog system, so that we can focus on other tasks. So, fortunately, exchanging arguments is made obsolete by better indexing schemes. Further, we can decompose arguments. Decomposing arguments is a workaround if a system doesn't provide deep indexing. For instance, if we have these 2 clauses, then argument indexing that only takes into account the principal functor can't tell the clauses apart, because the principal functor is f/1 in both clauses. However, we can again use an auxiliary predicate in such a way that also shallow argument indexing can tell the clauses apart. For example, in this concrete case, let's describe one level of nesting in the main predicate, and let's pass the remaining term to the auxiliary predicate p underscore. And the new argument is now a term that's not as deeply nested. And the 2 clauses of the auxiliary predicate can be told apart also without deep indexing, because their respective principal functor is g and h, which are different functors. And importantly, also this change retains full generality. I mean that we can still use the predicate in all directions to generate, test, and complete solutions. So decomposing arguments may be useful. However, if your Prolog system provides deep indexing, then it's quite unnecessary. And further, we can use legged arguments. Legged arguments are a bit similar to what we have just seen, in that a legged argument often arises from decomposing a term. And it's called legged because we carry along information via arguments that, in a sense, lag behind the new main arguments. For instance, let's describe the last element of a list. So let's define a relation list underscore last, and let's consider the cases. First, what about the empty list? Well, clearly an empty list doesn't have a last element. So this predicate certainly doesn't hold for the empty list. And we don't write down what doesn't hold, we only write down what holds. So let's consider the case where the list has exactly one element L. Then the last element of the list is of course L. And if it has 2 elements, then the second element is the last element. If it has 3 elements, then the third is the last element, and so on. So in general, if the list has at least one element L and the tail is ls, then the last element of the list is the last element of the tail. So the first element L doesn't even matter, so we use an anonymous variable for it, and that's it. And in this example, the first argument of the first clause is a special case of the first argument of the second clause. We say that the term is syntactically subsumed, or simply subsumed. And the second argument is trivially subsumed, because the second argument is a variable in both clauses. And therefore, no amount of argument indexing can help to distinguish the clauses. Also, deep indexing doesn't help here, because the second clause head syntactically subsumes the first one. And so, every time the first clause head applies, the second one also applies. And therefore, when we post, for example, this query, then we get a solution and the choice point remains, because both clause heads apply. And on backtracking, we get false. So there are no further solutions, and this means that the choice point was redundant. So to benefit from argument indexing, let's consider both cases at once. That is, let's consider a list that has at least one element L and the tail ls. And let's relate that list to its last element. And for this, we use an auxiliary predicate, let's say list last underscore, where the arguments are the tail ls, the first element L, which is the lagged argument, and the last element of the list. And for the auxiliary predicate, we distinguish two cases. First, let's consider the case when the tail is the empty list. Now, from the perspective of this auxiliary predicate, the lagged argument is the immediately preceding list element. Let's call it pref for previous. And when the tail is the empty list, then the last element of the list is of course this previous list element. And second, if the tail has at least one element L and a tail ls, then the immediately preceding list element doesn't matter for describing the last element. So we simply use an anonymous variable, and the last element of this list can be described in terms of this auxiliary predicate. Namely, it's the last element of the tail ls, where L is the immediately preceding list element. So if this relation holds between ls, L, and last, then last is the last element of the list in the first argument. And with this definition, our query yields one solution as before, and now it's deterministic, because argument indexing can now distinguish the cases, because the empty list nil and a list with at least one element have different functors. Okay? And we can shorten this definition, because we can say that the last element of the list with head L and tail ls is defined by folding from the left using an auxiliary predicate, say next underscore, over the tail ls with the head L as the initial state and the last element last as the final state. And we define the auxiliary predicate in such a way that it takes the current list element L as its first argument, it ignores the current state, and it uses the current list element as the new state. So this is an equivalent and shorter definition, and it therefore also shares all the same advantages. For instance, when we post this query, we get deterministic success. And at the same time, we can also post the most general query and get answers for increasingly longer lists on backtracking. So this definition is general and efficient in the sense that we can use it in multiple directions, and it's deterministic when possible. So lagged arguments can help us to make argument indexing applicable. And when lists are involved, then the code can sometimes be shortened with the meta predicate fold from the left, as in our example. And finally, we have reification. Reification stems from the Latin word res rei, which means thing, matter, affair. So to reify means to turn it into a thing. And in our case, this means that we turn the truth value of a relation into a Prolog term, so that we can reason about it explicitly. and so that it becomes amenable to argument indexing. For instance, the predicate zCompare lets us reify relations between integers. And as an example use case, let's consider the relation between an integer n and its factorial f. So, for example, the factorial of 0 is 1. And further, f is the factorial of n if n is greater than 0 and so on. And when we now query, for example, what is the factorial f of 0, then this first argument, 0, unifies with 0 in the first clause and also with n in the second clause. And accordingly, we get the solution f is 1 and a choice point remains. And on backtracking, the Prolog system tells us that there are no more solutions. So the choice point was redundant. So ideally, a choice point shouldn't even have been created here. And one way to ensure this is to reify the relation between integers using zCompare with 3 arguments. First, a Prolog term denoting the comparison. Second, an integer, in our case 0, and another integer, in our case n. And zCompare is a CLP z predicate that tells us in its first argument whether the first integer is less than, equal to, or greater than the second integer. And importantly, zCompare is a true relation and it works correctly for variables and also for instantiated arguments. And when we pass these arguments to an auxiliary predicate, say n factorial underscore, then we now benefit from argument indexing, because now we can symbolically distinguish the cases. If n is equal to 0, then the factorial is 1. And if n is greater than 0, then the factorial f of n, and so on. So this means that using zCompare, we have reified the comparison in that we can now reason explicitly about the cases less than, equal to, and greater than, using Prolog terms. And for our example query, argument indexing now detects that only one clause applies, and so it succeeds deterministically, without having created a choice point. And importantly, the predicate is still completely general. So for instance, for the most general query, the first and the second clause apply. And so we get the first solution and also others on backtracking. So again, the definition is general and efficient in that it can be used in all directions and it's deterministic when possible. And related to reification, we can also index diff, because sometimes we want to index on syntactic equality of terms. For instance, suppose we want to remove a term from a list. So first of all, that's not how we talk about relations, because remove is very imperative wording and it suggests only one direction. So let's rather say that we relate a list ls0 to a list ls. And ls is like ls0, but without a term t. So we have list without for the empty list nil, no matter what t is, ls is also the empty list. And for a list with at least one element L and tail ls0, we have that ls is like the list in the first argument without t if L and t are equal, and ls is like the tail ls0 without t. And alternatively, the relation also holds if L and t are different using diff, and ls, just like the list in the first argument, has the head L, and the tail of ls is like the tail of the list in the first argument without t. And that's it. And clearly, the two recursive clauses are mutually exclusive, because in one clause, L is equal to t, and in the other clause, L and t are different. And ideally, argument indexing should be able to tell the clauses apart. So first of all, let's pull everything we can into the actual arguments. For instance, we can pull this explicit equality, L is equal to t, directly into the clause set by simply replacing this T with L, wherever it occurs in this clause. Because we know that this clause only holds if L and T are equal, right? So we can simply use the same variable for both. And analogously, also for this explicit unification, this states that ls is the same as the list with head L and tail ls1. And so we can simply use that term directly instead of ls. So instead of ls, we write that list. So this means that we can now use ls instead of ls1. So now we have pulled all unifications into the clause heads, which is something that the Prolog system could, and in my opinion also should, have done for us. But even so, argument indexing still can't distinguish the last two clauses, even though they are mutually exclusive, because one clause head is subsumed by the other one, at least for the first two arguments. And so every time the first one applies, the other also applies. And neither deep indexing nor multi-argument indexing can distinguish the cases, because the only distinguishing factor is this diff goal, which states that one of the clauses only applies if L and T are different, while the other clause only applies if L and T are the same. And of course the program is still perfectly usable. So for instance, if we ask Prolog, what is the list ABC without B, then we get the correct solution. It's AC. However, a choice point remains, and only on backtracking we're told that there are no further solutions. So the choice point was redundant, and that's bad for performance. And making such cases deterministic while retaining full generality used to be a very tough challenge for Prolog programmers. So it's no trick to retain full generality, because that's what we just did. And it's also no trick to make it deterministic. But the difficulty is to achieve both at the same time. And this used to be a really tough problem. And the good news is that recent developments let us now easily express such situations in such a way that our programs are general and efficient. So let's simply write all this as the list ls is like the list in the first argument without t if, and now we use the predicate if underscore with three arguments. If L is equal to t, then ls is equal to ls1, and otherwise ls is equal to the list with head L and tail ls1, and ls1 is like ls0 without t. And further, we can shorten this all using the dedicated meta predicate t-filter. The list ls0 without t is ls if ls comprises all elements of ls0 that are different from t. And importantly, the definition retains complete generality. So we can, for example, use iterative deepening to generate answers for increasingly longer lists. And on backtracking, we get a fair enumeration of answers. And at the same time, queries are deterministic when possible. So for instance, when we now ask, what is the list ABC without B, then we get a single solution, and this is now deterministic, and that's good for performance. And for more information about if underscore and related predicates, see the paper Indexing Diff by Ulrich Neumerkel and Stefan Kral. And these predicates, which are based on reification, are all available in library Reif for several Prolog systems. And newer Prolog systems, such as for example Scryer Prolog, already ship with this library. So these are the most important methods to benefit from argument indexing. And these three of them, that is, pooling unifications into clause heads, exchanging arguments, and decomposing arguments, should happen automatically. Or they are made obsolete by better indexing schemes, such as JIT indexing. So this leaves three essential methods that are worth knowing: using clean data structures, legged arguments, and reification. And this of course raises the question, what else can a Prolog system do for us? That is, is it possible to automate also some of these things? And of course, the answer is yes. For instance, at least in theory, a Prolog system could automatically detect whether a legged argument could be used to improve determinism properties of a predicate. And a Prolog system could automatically apply such code transformations. However, there's a clear trade-off between convenience for application programmers on the one hand and complexity and overall speed of a Prolog system on the other. So an implementer of a Prolog system must strike a sensible balance between simplicity of the system and useful performance optimizations. And a sensible guideline for implementers is that a good Prolog system makes declarative Prolog code fast, because the declarative nature of Prolog is of course a great attraction. So it's good if declarative code is fast. And moreover, declarative code is quite easy to reason about and also easy to rewrite. And that makes many automated optimizations feasible. For instance, let's consider compiling disjunctions to clauses. Suppose we have a disjunction like this. Then this doesn't benefit from argument indexing, but it's easy to ensure that it does, because what we have here is simply a symbolic disjunction between A, B, and C. And to benefit from argument indexing, we can simply rewrite the disjunction by using a predicate like D, where the distinction is made in the first argument of each clause. And of course, ideally, this translation happens automatically. But on the other hand, too much automatic rewriting can also make it difficult to reason about our programs. And of course, it also makes a Prolog system more complex. And therefore, there's a limit for what we can realistically expect from a Prolog system regarding automatic performance improvements. And therefore, we must sometimes manually ensure that we benefit from argument indexing. And this is the reason why it's important to know these techniques. So I recommend that you read your Prolog system's documentation to find out more about its specific implementation of argument indexing, so that you know what it offers and how you can benefit from it. And also, I highly recommend that you ask your Prolog vendor to implement any performance improvements that you find important, because only dissatisfaction begets progress. And so I ask you to please be dissatisfied. I mean, not in the sense of pointless whining about the situation and changing all your programs to suit your Prolog system, but in the sense of aiming to fix the root causes of issues. So, I mean, for example, that if you find that your programs could benefit from a better indexing scheme, then you should create a self-contained benchmark or test case and report it to your Prolog vendor, and suggest improvements to the Prolog system from which many others will also benefit.